It's always great to come back to MIT and certainly to be a part of the day here today. And I really enjoyed Dr. Ting's presentation because as we're at JPL, you know, one of the things we're really about is science and answering those hard science questions and developing the capabilities and the systems and the instruments that ultimately help create the future, I think, that we just heard about. But also finding things that we didn't understand and saying, well, how does that fit with our current knowledge? So that's what drives us, and I would also say I love the theme here of Beyond the Cradle, because I would offer that we already are beyond the cradle robotically. So here's a little snippet of that.
InSight is now traveling at a velocity of 2,000 meters per second. InSight has passed through peak deceleration. Telemetry shows the spacecraft saw about 8 Gs. InSight should now be experiencing the peak heating rate. Ground stations are observing signals consistent with parachute deploy.
Marco Alpha, Marco Bravo, maintain lock status.
Altitude convergence, the radar has locked on the ground.
Yes.
Standing by for lander separation. Lander separation commanded. Altitude 600 meters. Altitude 400 meters. 200 meters. 80 meters. 60 meters. 30 meters. 20 meters. 17 meters. Standing by for touchdown. Touchdown confirmed.
I must say that between 16 meters and hearing nothing for 15 seconds was like the longest 15 seconds of our lives. But again, we go to explore. We go to really set the foundations for our future moving off the planet, if you will. And I love our first selfie of InSight, taken with the camera on board the robotic arm there. If you don't know, InSight's a mission to really understand the interior of Mars with a seismometer and a penetrator. We placed the seismometer on the surface with our robotic arm. First time we've ever put something off the spacecraft onto the surface. And this is our 8th successful landing on Mars, and it never gets easier, frankly, and it never gets less exciting. So the seismometer is placed. It's doing great work in terms of measuring movement within the crust and within the surface. And then, I'm not sure what happened to my, whoa, can we fix that? Where's the guys in the back? Okay, well, hopefully we'll get back to the normal slide mode. But so what you see up in the left in the small picture is the penetrator. It's a penetrator that's really like a pile driver that's supposed to force its way below the surface, ideally about 5 or 6 meters, and ultimately when you're that low, any temperature that you measure is coming from the core of the planet, so we can understand the core temperature. Now, as Dr. Ting pointed out, when you go to anywhere outside of the Earth, and often on the Earth, you find that things aren't exactly as you anticipate. So our first day of driving the penetrator down, we expected to go about 40 centimeters. We went about 23. And apparently we've hit a rock. So we pounded it for about 4 hours the next day. Didn't really make a lot of progress, except it started canting about 15 degrees. So now we're in the middle of understanding what our options are. So can we perhaps pick it back up and move it? That's a little tricky. Can we somehow try to maneuver around the rock? So you go to learn these things. And when you're exploring, you don't know exactly what you are going to find. But that's just a part of what we do. But that's kind of the latest on that. And of course, Curiosity has been operating on Mars since August of 2012, so coming up on 7 years of surface operations on the planet, and really incredible findings. We've talked about, the future and going to Mars, and you heard from Maria yesterday about the water there, and it's been an incredible mission of discovery and really understanding and paving the way for us to go there with humans. You heard Thomas Zurbuchen and Charlie Bolden talk about in the 30s. That's kind of where we want to be in the future. And our robotic explorers have paved the way for us to truly leave this cradle and understand what it's like when we get there. So this is just a great picture of the sand dunes as we've driven around. And you know, you think driving around another planet, you joystick this thing, you drive around, it's all fun. This is not easy stuff. You have to survey where you are, you have to build the command plan, you have to send it up, you have to see if the rover did it the next day. It's a pretty excruciating process. But again, Maria talked a lot about the water, and this is a great picture of the sedimentary layers that are formed by large quantities of water over a long period of time on the surface of Mars. And so we've shown that that was indeed the case in the past. And the question, of course, is there extant life that's still there now, or could have been in the past? And that's what we continue to search for. That will be a key component of Mars 2020, a lot of more advanced instruments to look for life. But in particular, the primary mission is to cache samples that we'll bring back to Earth. But also another primary mission is to, again, start to lay that foundation for human exploration. We're carrying an experiment called MOXIE, which is really the Mars Oxygen ISRU experiment, in situ resource utilization. So this is our first time to go to the planet and create oxygen from the atmosphere on the surface. So we've been developing that instrument at JPL. It's pretty much wrapped up in terms of being complete, and we're getting it into integrated test. And so we're very much looking forward to really taking those first steps to being able to go to Mars in the future and create the oxygen you need to live and to utilize for other purposes. So again, a great first step there. And then we're also going to go and develop the first aero vehicle on another planet. This is our Mars helicopter. How many of you know what percentage of the atmosphere Mars is compared to Earth? 1%. Yeah, 1% of Earth atmosphere. So think about trying to fly a rotorcraft in 1% of the Earth atmosphere. Frankly, we weren't sure exactly how we were going to do this. It's only 2 kilograms. It's not really big. It's got a high-definition camera, and its purpose is to go out and kind of scope out ahead of the rover so we can see beyond the horizon, if you will, and prepare for the traverse. But we've proven we can do it. So this is our vacuum chamber at Mars atmosphere with the helicopter last year, showing that, yes, indeed, we can indeed do this. We can control it. We can make it work. And it does work. So this is 1% of Earth atmosphere. And we have actually completed the flight model now, the helicopter. We've delivered it to Lockheed Martin. They're building the container that will put it on the rover. And so we're in that integration right now. So, yeah. But as you think about human exploration, you want to enhance the human's ability to explore around them. And we certainly think in the future, this is one way you do that, is you have this whole fleet of robotic systems, aero vehicles, maybe even lighter than air, although that's tougher in 1% atmosphere. But things, yeah, and on the moon, but things you can do that expand the human's ability to understand his environment and where he's living, where he or she is living. So, but this was very successful, and again, as I said, we're ready to go and show that we can do this. So I won't let it land. I'll keep going here. So, as I said, another part of Mars 2020 is bringing samples back. I think you heard yesterday about the importance of having those lunar samples and what we learned from them. We've done a lot with Curiosity. We've done a lot with Spirit and Opportunity. We'll do a lot with 2020, but frankly, there's just certain things you can't do with a robotic system in great detail on another surface. So we want to bring samples back. That's what 2020 will start in terms of caching samples in these small tubes, hermetically sealed, etc. And ultimately, in the mid-20s, send a mission there to go to the surface with a fetch rover, pick up the samples, put them on an ascent vehicle, put them into an orbiting spacecraft, bring that spacecraft back to Earth with the samples. Very complex, and but again, that first step to really giving us greater understanding of the Mars environment and surface, and also preparing for human exploration of Mars. So this was in the 2020 budget for the first time. We've been doing some pre-work on this already, but now it's officially in the President's budget, so we're moving forward with this program. And another thing that I think in many ways was science fiction in the past, but now, in my opinion, is allowing us to explore the greater solar system in much different ways than we have in the past, is electric propulsion. This is our Dawn spacecraft we built in partnership with Orbital Sciences. It has been in orbit around the Ceres asteroid, the largest asteroid, really a planetoid. For the last couple years, it actually ended its mission last fall as we ran out of reaction control fuel in order to keep it properly in orbit around Ceres. But just amazing discoveries in terms of, here's an asteroid that has ice, it has cryovolcanoes, it has water, or at least frozen water. So again, something that we didn't even know before we went there because all we could see was kind of this blurry image from our telescopes. And yet we're finding that there's ice and water throughout the solar system. And again, 20 years ago we thought, hey, only Earth has water. So, but electric propulsion is one of those things. In fact, on Mars sample return, that's probably what we'll use to get out to the planet and come back because of the high ISP that we can get from that. But you can see over 50,000 hours that we put on this ion engine. And it worked flawlessly. We really never had a problem with this thing. So I think that's really a game changer in terms of exploring. It takes time, but it gives you the capacity to go long and go far and do incredible things. And we move into the outer planets. Europa is that moon of Jupiter, which is a water moon. It's very interesting, and we're excited to go back there with Europa Clipper. And someday, hopefully, a lander. That's still to be funded, if you will, but Clipper is funded for a launch in 2023. It's an icy surface. We believe it has more water beneath it than the entire Earth, like 2 to 3 times the amount of water. So, of course, where there's water, there could be life, and that excites the scientists in terms of our future. Enceladus, that moon around Saturn, shooting geysers of water up from its southern pole. We actually flew Cassini 13 miles above the surface of Enceladus through the plumes and measured them. But obviously, we want to go back there and do more exploration. So, again, as we go out into the solar system, there's water available to support us in our exploration. And that promises a very exciting future. Psyche is an all-metal asteroid. We're designing a mission with Loral Space Systems to go there. Scientists believe it's a planetary core, that now we can directly look at a planetary core where the surface has been stripped away over the years by asteroidal bombardment and learn what does a planetary core look like. So that's very exciting. And then we talked about democratization of space, and I think these smaller spacecraft are going to allow us to do that. Marco was our first interplanetary CubeSats that we flew along with the InSight mission. They actually deployed from the booster that we shot InSight to Mars with. So it kind of flew along with InSight to Mars and acted as a communication relay. And without those, we would not have had that real-time data of the entry, descent, and landing of the InSight mission. So just think about 2 CubeSats transmitting data back from Mars, and they're about this big. And we had to rely on them to get that real-time data. So I think there's this revolution in CubeSats that really is going to change how we can put systems into orbit that do real missions. This is a CubeSat that we developed, first Ka-band radar on a CubeSat, and it's doing science. It's measuring precipitation formation inside a cloud. The Ka-band is where we can do that, and it's doing incredible work. It's giving us incredible data. And now if we put a fleet of these in orbit, we can get time phase understanding of precipitation formation inside a cloud at a very low cost that we couldn't do with a larger spacecraft because you need a lot of them. And this is even going out to interplanetary exploration. This is a design we've come up with that we're proposing in partnership with India on their next Venus mission to actually put a CubeSat that will fly into Venus's atmosphere and take measurements as it goes into the atmosphere and do, again, real science for us. So I think that's really going to change the face of space exploration in many ways. This is a mission we're launching in 2020, Lunar Flashlight. We heard about the water on the moon. This is using a laser to actually look for that water and measure what it is in those dark craters on the surface of the moon. And so we're using a CubeSat to do that and to do real science. And of course, looking beyond exoplanets, we're all excited about that. This is our next telescope that, if it's funded by Congress, will go out and ideally image an exoplanet and perhaps find atmospheres that are capable of supporting life. And we're designing the next generation of telescope that will go beyond that and will image even more exoplanets. And of course, we like to look back at Earth, and we do a lot of things to do Earth science. And I know I'm getting the hook here for we got to get going. But and ultimately, there's a lot of data coming at us that we have to manage. So with that, if you want more, there's our strategic plan, and that's our motto: Dare Mighty Thing. So turn it over to Loretta.